With the transformer architecture in literally every corner of our lives, whether we're generating new frames while playing our favorite video game, creating AI avatars of ourselves, or even receiving recommendations from YouTube's new algorithm. Yes, they're using LLMs now, surprise, surprise. It's clear that Vaswani and his co-authors were onto something when they claimed attention was all we needed in their seminal 2017 work. Flash attention, what we'll be discussing today, builds directly on that breakthrough and represents an advancement of the same order of magnitude as the original attention paper. Attention allows different tokens of an input sequence to talk to each other, whether it's text, images, or video. Given that this then enables a transformer to do what it does best, extracting all relevant semantic meaning from the input, any speedups to this operation greatly affects training and inference. Flash attention is a faster way to compute attention, one that takes advantage of the memory hierarchy that is innate to our modern accelerators. The best part? It's completely open source, and the speedups it enables aren't limited to enterprise-grade GPUs that are tens of thousands of dollars. On an RTX 3090, flash attention enables a speedup of over 4x. Using it is as simple as calling this one function from PyTorch. It's literally a free performance gain with no hacky approximations or sacrifices of any sort. The reason why this algorithm is so beautiful is because its inspiration wasn't from some elusive mathematical theory that only makes sense to a select few. Flash attention is an I/O-aware algorithm that is, quote, carefully accounting for reads and writes to different levels of fast and slow memory, end quote. It's a marriage between pure math with elegant proofs and the actual silicon that we can physically hold in our hands. It illustrates that algorithms can't just exist in a vacuum, but must also be influenced by the constraints of the hardware that enable them to run at a global scale. We'll start things off by first reviewing the original scale dot product attention operation, then understanding how the memory hierarchy affects the way we write algorithms, followed by us developing the actual flash attention algorithm. Finally, we'll wrap things up with how we can enable this speed up for ourselves. While the attention mechanism itself gave birth to a whole new era of machine learning, the original algorithm was quite slow. Horribly slow, in fact. Let's understand why. On screen, I have the equation of the attention operation. In code, that equation looks something like this. We're not going to touch upon multi-headed attention here, but extending everything we learned from today to multiple heads is trivial. Our input sequence contains B batches, each of a sequence length of S, and each token in our sequence has been mapped to a vector of size d, which is our model's hidden dimension. If you're a little confused about the theory behind why we do things like this, I cannot recommend highly enough Andrej Karpathy's video where he implements the attention is all you need paper from scratch. Also, for the rest of the video, I'm going to omit the square root term because it's just a division by a constant. So where is the inefficiency in this code? Well, we have control over the batch dimension, and even recent LLMs haven't really scaled the hidden dimension past 10k or so. The real issue comes from when we scale the sequence length, which has reached into the millions these days. We can see the space complexity of the weights matrix is O of n squared with respect to sequence length, and the matrix multiplication operation between it and the V matrix has a time complexity of O of n squared times d. Taking a trip back to our data structures and algorithms class, we know that quadratic scaling is pretty bad and should be avoided if possible. If we had a square matrix with size 1,000,000 by 1,000,000 at bfloat 16 precision, so 2 bytes per value, that matrix alone would require over 2 terabytes of VRAM. As the sequence length of our model increases, this code, with all of its operations with the weight matrix, becomes more and more of the bottleneck for efficient training and inference. Here's a simple diagram of how the memory is laid out in our GPUs. All of our data lives here in HBM or high bandwidth memory, sometimes referred to as VRAM. Funnily enough, it's this memory that has the lowest bandwidth on our diagram. Well, only because CPU memory isn't depicted. Up top, we have our SMs or streaming multiprocessors, the hardware that actually does the computation, like the additions and multiplications in our matml operations, and each SM has its own registers and L1 cache, which cannot be accessed by other SMs. However, in the middle is our L2 cache. This memory is much faster than our HBM and is shared by all of our SMs. While it's more than our L1 cache, it's nowhere close to the amount of VRAM we have. According to Hazy Research, a research group based out of Stanford, the HBM's bandwidth for NVIDIA's flagship H100 is 3 terabytes per second, the L2 cache has a bandwidth of 12 terabytes per second, and the L1 has a bandwidth of 33 terabytes per second. That means the L1 cache can move data around over 10x faster than HBM. Unfortunately, we only have around 256 kilobytes of it, where for HBM we have 80 gigabytes. And while I couldn't find reliable latency metrics for the H100, I've listed the ones for the A100 on screen. Again, we can see an order of magnitude difference between L1 and HBM. The moral of the story is we should use our L1 cache whenever we can, L2 whenever we can't, and HBM only if we have to. For each thread in an SM, they should ideally access the same data from L1 to avoid a trip to L2. However, when there's a cache miss in L1, an SM will save the data in our L2 cache. Then, if another SM were to try to fetch the same data, it wouldn't have to make a trip all the way down to HBM. In our code, each time we perform an operation, the operands are going to be pulled from HBM so the SM can do the operation, and then the intermediate result will be written back to HBM. This is because PyTorch runs in eager mode by default, so it performs operations in a greedy fashion, without any regard for upcoming operations. It'll see the query linear operation, pull our input sequence and the weights of that linear layer from HBM, perform the matmul, then write the Q matrix back to memory. Then, it'll see the key linear operation and pull all the relevant values from HBM and then write the result back to HBM after the calculation. Sure, some values from our input sequence may still be cached, but there aren't any guarantees, nor would it be enough for it to actually matter. Then, it'll see that it needs to multiply the results of the previous two operations and pull them back again from HBM. Okay, you get the point. Once we materialize our weights matrix, we have to move that giant thing around too. Don't forget that we have the softmax operation, linear layer for our value matrix, and final matmul between those results and the weights matrix left. The crux of the problem is that no matter how we do things, this massive weights matrix must be fully materialized, which means S times the number of bytes of our data type amount of memory must be allocated somehow, inevitably in HBM, or we end up facing the dreaded or the out of memory error. In order to navigate this challenge, we need less reads and writes to HBM. It'd be ideal to take as many values from the original Q, K, and V matrices, saturate our cache, perform all of the operations on them while they're still in our cache, and then write only the final result back to HBM, never to be touched for the rest of the attention computation. We essentially need to fuse all of these operations into one massive one that doesn't yield these large intermediate results, like the weights matrix. Before we jump into flash attention though, let's use a simpler operation, one used by the attention mechanism to see how our hardware constraints can influence how we write algorithms, the softmax. This is the equation of the softmax. It takes in an input vector, raises e to each of the elements, and divides everything by the sum of the exponentiated elements. One thing to note though is that due to the risk of overflow, we'll actually subtract the vector's maximum value from all the elements. If x is equal to 12, we've already exceeded the max value for float 16 of 65,504. This doesn't change the output though, because a subtraction in the exponent is just equivalent to dividing by the base raised to that second number. So we'd just be dividing the numerator and denominator by the same value. So a naive implementation of this new formula requires 3 passes of our input data. 1 to get the max of the input vector, 2nd to calculate the sum in the denominator, which requires us knowing the max, and 3rd to actually divide each element by the calculated sum. This is not good. Obviously, for really small input vectors, the entire thing would fit in our faster cache. But remember that in machine learning, scale is everything, which means each separate pass over our data would require going all the way back to HBM in order to fetch evicted values. The challenge here is the order of operations. We have to iterate over all of the elements to calculate the sum before we're actually able to divide each element by the final sum. We can't just calculate the softmax of all the elements in a vector in parallel. Thankfully, some researchers from NVIDIA published this paper in 2018 titled Online Normalizer Calculation for Softmax, which outlines how to calculate the softmax in an online fashion. It does so by utilizing an intermediate buffer that keeps track of both the running max and the running sum. Let's see how it works. We're going to achieve this via an expanding window, starting from the first element. At the beginning, our running max is equal to the first element, and our running sum is equal to e raised to the power of the first element minus the running max, which is just the first number. So we get e to the 0, which is 1. M sub I represents our running max up until the element at the ith position. D sub I represents the running sum up until that position. Next, we expand our window to 2 elements. Our running max remains the same in this case, but we have to add to our running sum e raised to the second element minus the running max, so e to the 2 minus 3. Note that I'm writing d sub 1 as a sum of multiple elements for now, but when we'd actually run this algorithm, this running sum will be kept completely evaluated and stored as a singular floating point number in memory. You'll see more of this throughout the rest of the video, only because I think it helps us understand the math better. Things get interesting when we expand our window to 3 elements. We compare 4 to our running max and see that we have a new running max. This means the elements of the sum in d sub 1 are now invalid. Is there an easy way to fix this without having to iterate through all of the previous values? Doing so may require us to go all the way back to HBM if those values have been evicted from our cache. Well, thankfully, calculating d sub 2 from d sub 1 is pretty straightforward. We can multiply the value of d sub 1 by e to the old max minus new max. Why does this work? Well, once we expand it, we can see that because of the rules of exponents, once we distribute this value, we can cancel out the old max in the exponents, resulting in the old values being subtracted by the new max. Now, we can simply add the new element to this running sum, making sure that we're now subtracting by the new max. Again, this is only efficient because we're storing d sub 1 as a single value while running this algorithm. The bottom equation summarizes our steps. All we had to do is multiply d sub 1 by e raised to the old max minus new max, or e raised to m sub 1 minus m sub 2, and add the new exponentiated value in order to get d sub 2. And that's it. No matter how large this vector is, the algorithm will never need to go back to previous elements to update the running sum or running max. And when we end, m sub I will hold the vector's global maximum and d sub I will hold the sum of all of the exponentiated values subtracted by the vector's global maximum. The final step would be to then take these two values and do one final pass over the vector, calculating the final output. Yes, it's still not one pass, but at least we've managed to cut it down from 3 to 2. Thanks guys for making it this far. I know that was a lot, but if any parts were unclear, please let me know down in the comments below. But remember why we're doing all of this. It's all because of the memory hierarchy. The less passes over our inputs we can make, the less trips to HBM we need. Now that we understand how the online softmax reduces the 3 passes to 2 passes, I have good news to share. For flash attention, we don't need the entire intermediate vector from the online softmax, so we're actually able to perform the complete attention operation in just one pass. Looking back at the equation for attention, the next operation after the softmax is a mapmul with the V matrix. Let's get started. For simplicity, let's take a single row that we want to perform the online softmax on, and a single column from the V matrix that we want to dot product the result of the softmax with. We can see our expected result at the bottom. Again, I've left the equation expanded, but in reality, this value would be a singular floating point number. The first iteration of our loop is trivial. We update the running max and the running sum as usual. But now, after we get the running max and running sum, we perform the softmax operation on our current element. Then, we multiply it by the corresponding element in our column vector to get our running result, or O sub I, which is an additional running total we're now keeping track of. For the second iteration, updating the max and running sum is straightforward, but since our running sum has changed, we need to update the running result without going back to previous elements. At the top, we have our current running result, or O sub 0. At the bottom, we have the new running result, O sub 1, which has our updated running sum. After substituting away this chaos with our m and d variables, we only need 2 operations to efficiently update our running result. First, we multiply what we have by the old running sum over the new running sum. Canceling out like terms yields us the following. Now, we can just add the new output from the softmaxed vector multiplied by b, which is the corresponding element from our column vector in our V matrix. Since our max value didn't change during this second iteration, M sub 0 and M sub 1 are the same. The final equation at the bottom summarizes what we did. When the running max hasn't changed, all we need to do is multiply by the old running sum and divide by the new running sum before adding the new component to our running result. Going back to the softmax plus dot product operation, we just learned the extra step required for when only the running sum changes. However, for the final iteration here, we see that both the running max and the running sum get updated. Let's take a look at how the math works here. Again, at the top, I have the running result from the second iteration. At the bottom is our final iteration's result. In order for us to properly update our running result, we need to perform a couple of operations that bring us from the top to the bottom without requiring us to revisit older elements from our inputs. Let's start off by multiplying by the old running sum again. After canceling like terms, we get this. Now that our running max has changed, let's use the trick from the online softmax to multiply by e to the old max minus the new max. After distributing and canceling out the m sub 1s, the result is each of the elements from our original input row vector being subtracted by the new running max. Finally, after dividing by the new running sum, we see that we're now able to add the new component to our running result, the part that's multiplied by c, the final value of our column vector. Let's take a look at the final equation summarizing what steps we just went through. Again, we can see the general case for updating our running result is to first multiply the old running result by the old running sum, then multiply by e raised to the old max minus new max. When the max doesn't change, this simplifies to e raised to 0. Then we divide by the new running sum. And finally, we add the new component to the running result, the next element from our softmax vector divided by the running sum multiplied by the element from our column vector. This is the core equation behind flash attention. It outlines how to keep our running result up to date when our running sum and max change. Because O sub I is solely a function of O sub I minus 1, the running max, running sum, and the current item in our column vector that we're multiplying by, we don't have to go back to previous elements in our input vector or our column vector. Well guys, we finally have all of the building blocks in order to see the final flash attention algorithm in action. Let's say this is our setup. We have the Q matrix on the left, the K matrix transposed on the top, the V matrix on the top right, and the output matrix on the bottom right. We can see that the longer dimension for our Q, K, and V matrix represents our sequence length, and the shorter dimension represents our hidden dimension for our transformer. Multiplying the Q and the K transposed matrices yields us our square weights matrix with dimensions of sequence length by sequence length. Remember, we do not want to materialize the weights matrix at any cost. As an example, take the third row of the Q matrix and the first column of the K matrix. Their dot product yields the first value in the third row of the weights matrix. Remember, for regular attention, we'd have to get the entire row before the softmax operation. Only afterwards would we be able to dot product it with each of the columns of V to get the third row of O. But we learned how to perform the online softmax followed by a dot product using our buffers at the bottom, and we're going to do just that. But this time, it'll be 2 times, one for each of V's columns. While our output row remains incomplete, assume it resides in our cache for now. We'll make the final trip to HBM once we've calculated the final result. Now we can move on to the next columns in our K matrix and the next rows in our V matrix and continue to repeat this process. We're not even adding anything that we haven't already covered. So after all of that, we have just one row of our output matrix. But remember why we went through all of this pain. The weights matrix was never fully materialized. This means at any given point, we only needed one value from the weights matrix along with our 2 running buffers. You might be wondering though, Sorish, it literally seems like we're doing more math operations than original. We have all of the math operations that's done from the matmults and softmax just like regular attention, but now we've added the running buffers, we're normalizing and denormalizing. Where are the compute savings? Well, that's just it. There are no compute savings. You're right, we literally are doing more computation. But the reason why flash attention is so novel is because it takes advantage of the fact that modern machine learning algorithms result in our hardware being more bandwidth bound than compute bound. This means the amount of time our SMs are waiting for data is too high relative to the time they're actually crunching that data. Our GPUs are fast, like really fast. But unfortunately, the memory bus on these devices just aren't fast enough to keep the SMs fully saturated. This means if we're able to increase our arithmetic intensity, or do more math, per operand, we'll be able to balance out the disparity between time spent waiting for data and doing math on that data. And flash attention does exactly that. It increases the number of operations we need by a little bit, but drastically reduces the amount of data we need to move. Briefly revisiting our memory complexity, the original attention had quadratic scaling with respect to sequence length. Flash attention, on the other hand, only has a linear memory complexity. And that's where the wall clock speedups stem from. So how do we use flash attention in our PyTorch code? Well, let's revisit what we had from earlier. All we need to do is replace these lines with this single one. Yep, that's literally it. The default backend for PyTorch's scaled dot product attention function is the flash attention one, assuming your GPU supports it. Otherwise, it'll choose another backend to ensure compatibility. You can also manually specify the backend you want to use if you so desire. Remember how I said earlier that PyTorch works in eager mode by default? Well, those of you familiar with Torch Compile may be wondering why we didn't just enable that. Rather than just greedily performing operations as they come and writing intermediate results to HBM, Torch Compile takes your model, creates an intermediate representation of it in the form of a graph, which allows it to look ahead at the operations that it'll need to do. It can then strategically fuse subsequent operations or kernels into one. For example, if we have a linear then a ReLU, there's no need to write the output of the linear layer to HBM and fetch it again for the ReLU. Since ReLU operates independently on each element of its input, PyTorch can simply perform the ReLU op while the values from the linear are still warm in cache, and then write the final output to HBM. Well, Torch Compile is great at finding these low-hanging optimizations, such as a linear followed by a ReLU, but unfortunately the algorithm we covered today is too advanced for a compiler to recognize and fuse, which is why we need to manually tell PyTorch that the lines we replaced is equivalent to Torch's scaled dot product attention operation. Maybe one day our compilers will be smart enough for this. This diagram from the paper illustrates the potential of fusing multiple separate kernels from GPT-2 into one massive one. This is where the 7.x speedup comes from. Well, unfortunately, there's a lot that we didn't get a chance to cover. First and foremost, we didn't cover the backward pass, which is kind of a critical component of the training process. And if you look under the hood, the official implementation of flash attention is still much more complicated than what we saw. The biggest one that I've omitted is probably tiling, which utilizes the L1 cache's ability to be reconfigured as shared memory, allowing for more manual memory management. Instead of operating on elements one at a time like we saw today, tiling allows us to grab small groups of elements at a time, using more of our cache proactively. Additionally, there have been two new sequels to Flash Attention, Flash Attention 2 and 3. Flash Attention 2 adds some more modifications to reduce reliance on shared memory and reduces some flops. This is actually the version PyTorch uses, not the one that we covered. Flash Attention 3 exploits some new hardware present in NVIDIA's H100. I do plan on making a future video where we will actually write the code for the Flash Attention algorithm with Triton, so stay tuned for that. But I hope the biggest takeaway from today was how algorithms meant to run at any sort of scale must be designed in harmony with the systems that will run them. Anyways, thank you so much for making it until the end, and I'll be back soon with future videos. Until then, see ya.